Okay, well, welcome everybody to the fourth SoFiE Seminar. Today we're very excited to have Rob Engle as our presenter from NYU Stern School of Business, and his discussant will be Professor Oliver Linton from the University of Cambridge. The format for today will be the same as in previous weeks. It'll be 40 minutes for the speaker, 10 minutes for the discussant, and 10 minutes for Q&A from you, the audience. During the presentation, Rob will stop once or twice to accept questions from the audience. So if you have a question, please use the raise your hand button down at the bottom of your Zoom screen, or use the Q&A box to ask your question. And then when there's a break to take questions, I'll either ask your question on your behalf, or hopefully we'll have time and I'll unmute your mic and then you can ask the speaker your question directly. So let's begin. Rob, if you'd like to share your slides, we can start.
Okay. Can you see that?
Looks great.
So ready? Okay. So this is work that I've been doing with Susanna Martins, who's now at Oxford, and it's a way of trying to understand the geopolitical risks that face investors. And this is a picture which is possibly one interpretation of what geopolitical risks are. I mean, this is the communist era sculpture, and it suggests that politics may be an important part of the financial landscape. But it's really unclear exactly how we ought to define geopolitical risks. And for example, is this really about politics or is it about economics? Is it about terrorism and military risks? Is it about cyber risks or things like elections, which are on a predictable schedule, and congressional actions and political movements? Is it about the level of risk or the surprise in the risk? And there are several approaches to how you would measure this. Some are using news stories from news sources like newspapers, and others are using financial markets. So here are a couple little quips that we could think about this. We are drowning in information and starving for knowledge. I like it. It's kind of why we do econometrics, and I think trying to make sense of the complexity that's around us and all the data. And that's sort of summarized by the Hasty, Tibshirani, and Friedman introductory notes in their book. The statistician's job is to make sense of it all, to extract important patterns and trends and understand what the data says. We call this learning from the data. Econometrics hasn't always sort of thought of that as what it does, but I think it is really what our most important contribution is understanding and interpreting and making clear what it is in the data that's important for our own behavior and public policy and so forth. So here's my introduction. If you look at the world map and color code it by volatility, which we do on VLab all the time, it's looked kind of like this for most of the last decade. It's been green almost everywhere, which means low volatility. This is from last fall, but you get the same thing in January. If you look at it right after Brexit, you see it turned red in a lot of different places. If you look at it in this March, you see a dramatic rise in volatility everywhere, except Mongolia, Venezuela. I mean, a few places where the markets may not actually be responding that well. But in any case, this is an example of how you think what we see in data is that volatilities move together. Volatilities of different asset classes move together, different countries move together. And you can see this when you look at sort of, these are Garch models of different asset classes. And even though some of them only have a little small peak during the financial crisis, you know, everything goes up during the financial crisis, and it goes up during the European sovereign debt crisis. And, you know, we don't really have good statistical models of how to do this. So the most common view of why this happens is because there are factors, financial risk factors, which have volatilities themselves. And so each asset is exposed to these volatilities because of their factor loadings, their betas on these risk factors. But it turns out that if you extract all the risk factors that you can think of, that in fact, there is a common component to the idiosyncratic volatilities, which doesn't go away. In fact, there are a couple of interesting papers that I've just referred to here. One is the Herskovich, Kelly, Lustig, van Neuberberg paper, and the other second is Connor Korchek and Oliver Linton, and then Hodrick, Ang and Hodrick, and as co-authors as well. So there's been a lot of interest in idiosyncratic volatility, but I think it's partly because it's not really so idiosyncratic as we might have thought. There's a common part of the idiosyncratic volatility, and that's what this is focused on. And it's also what the Connor Korchek and Linton paper is focused on. Okay, so, but then from a statistical point of view, we know that it's very hard to forecast asset returns, but it's not so hard to forecast volatility. And we're going to actually apply that in a new kind of more cross-sectional sort of way. We're going to try to understand why asset volatilities are correlated. And there are two ways correlations can arise. One is that there are predictable movements where one sector is a leading sector and that produces volatility in other sectors. But at least in financial markets, that doesn't seem to be the best explanation. It doesn't seem clear that there are some assets which have volatilities which are important predictors of volatilities and other things. It's more that these are contemporaneous shocks. And so we're going to be looking, first of all, and in this paper only, at the shocks to, how much correlation is there between the shocks to volatilities across different assets and asset classes? Okay, so we're going to develop something which I call GEOVOL, and it's a latent factor that we're going to try to measure. It's a volatility factor that affects all financial assets, asset classes, and markets at the same time. And when it has a high value, what that really means is that all these assets have surprisingly high volatility shocks at the same time. And when it has a low value, they have a low shock at that time. So we're going to identify this statistically, and then we're going to go back to see whether it looks like political and military or terrorist shocks and what it is that makes this GEOVOL move. So what is a shock to volatility? Well, if you think about the returns to an asset, subtract off the mean, and this might be a day, square it, that is a shock to the return. And if we divide it by what it was predicted to be, it becomes a percentage shock to the return. And we think of this little e squared is what we have typically called standardized residuals from a Garch model, and this is the square of them. And so the idea that the shocks to volatility are correlated means that these e squareds are correlated across assets in a cross-sectional sort of way. If we try to look at the expected value of the e squareds, given past information set, if this is really the variance and this is the conditional mean, then conditional variance and conditional mean, then the expected value of this should be equal to 1. So we already know a lot about what these e squareds ought to look like. what we, and I should say that these E's should be also uncorrelated across assets if we've taken out all the relevant risk factors ahead of time. So these are idiosyncratic shocks because we are extracting the market factors, the risk factors that are presumably relevant and explaining the cross-sectional correlations, but that doesn't eliminate the cross-sectional volatility. So here's the basic model that we use in, or at least think of in finance, that we've got some risk factors, which are some linear combination of asset returns, and the asset returns have factor loadings, these betas on the risk factors. They also have a risk-free rate. And then there's a covariance matrix of the shocks to the idiosyncratic errors, which are going to be uncorrelated, but heteroscedastic. And each one will have its own heteroscedasticity process. But these E's that come out of this should have expected value 0 because there is covariances of 0 because we've taken out all the risk factors, which by definition are the factors which are responsible to give us correlations. Okay, so this is familiar territory. What's not familiar is the behavior of the squares of these E's. And so it's really like the original idea behind Arch and Garch models, that returns are serially uncorrelated, but they're not independent. And in the same way, these E's are going to be cross-sectionally uncorrelated, but not independent. So what we're going to, the factor that we are going to see and measure is the fact that E's are not correlated, but their squares are correlated. That means that the volatility is high for all assets at the same time. And it might be low for all assets at the same time. But if you don't know when this is going to be, then all you see is that the average, on average, is 1. So we're going to be interested in the correlation between squared idiosyncratic, between squared volatility shocks in one asset and squared volatility shocks in another asset. And you can calculate these correlations, and we're going to do that, and you'll see that they're bigger than 1. So that is something, that's a new feature that's not in our standard asset pricing models, but is quite very apparent in the data. So one of the things, so I'll show you one of these matrices in just a second, but basically we find that all the correlations are almost all positive, but they're not exactly, they're not equal. So we're going to have a little richer model than just having them, everything correlated with each other. So I'm going to write down a statistical model for this, and I'm going to define what I mean by this GEOVOL. And GEOVOL is, by its name, is really thought to be a volatility, but I'm going to be interested in writing down a model for its square, which is its variance, which is, well, it's a second moment, but anyway, X, and I'm going to call X the square of GEOVOL, and this is going to be a random variable which has conditional expectation of 1 and a variance which is equal to V of t. So its variance doesn't have to be constant over time, but its conditional mean does have to be constant, and it has to be 1. And so from this equation, it's clear that because the information set here is presumably all past observations on returns, there's no way to predict when this GEOVOL event is going to be high. in fact, it's a slightly, I can put in a slightly weaker condition, which is that the expected value of X conditional on the past of any one asset is equal to 1. And that will turn out to deliver the same sort of thing. So this says you can't really predict X based on the past of any one asset, but maybe you could by the past of everybody, of the collection of assets. And I think there's some statistical evidence for that, which I'm not really going to focus on today, but it's a little weaker assumption than the top one. So here's the kind of model that we're going to look at. The variance of these E's is going to have a factor structure so that there is some factor loading from each asset that gets multiplied by the difference between X and its mean, which is 1. And then because the variance of this has to be equal to 1 unconditionally, that is when you put X equal to its expectation of 1, then this E has to have a variance of 1. So this is a very simple but easy to use expression for how the latent variable X changes the volatility. And since X has no subscript on it, it changes volatilities of all these assets at the same time. It turns out with this kind of specification and either of the assumptions that I showed you about X, that you still have the expected value of the epsilon E prime is still equal to the identity matrix. And from this expression, we know that if S is between 0 and 1, that X will automatically, that the variance of EJ will automatically be positive if X is positive or non-negative. So how do we interpret this X thing that I've defined? Well, first of all, it gives us all E's with a variance of 1. On some days, the squared return is bigger than 1, some days is less. When X is large, we expect they're all to be bigger than 1. We expect them to be bigger. And so how much bigger would they be? Well, it depends on what S is. If S is equal to 1, and you've got a value of X which is 4, then the standard deviation of returns would be the square root of 4 or 2. If S is 0.1, then it would be the square root of, well, it's 2 times 0.1 plus 1, take the square root, you get something which is only slightly bigger than 1. So the smaller S is, the less impact X is going to have on the standard deviation of returns. Okay, so how did I do? Is this a, maybe this is a good time to see if there are questions. I'm going to talk about how to estimate this now. And
well, you've done too good a job, Rob. We have no questions just yet.
Perfect. Let me keep going then.
Okay.
Okay, so I'm going to now convert this into a data generating process. So if you let these epsilons be IID, and in the Monte Carlo they're going to be normally IID, then this looks like a Garch model. It says that the EJs are the square root of the conditional variance times a random shock, and this G would be given by this expression we just talked about. So this is a cross-sectional heteroscedasticity model. As S's are different from each other, the variance of each of these epsilons will be different. And over time, they will be different also because the X's are different over time, even though the SJs would be constant over time. So from this, we're able to calculate what the covariance matrix of squared E's really looks like. And we can look at the variance of E, and the interesting thing is to look at the variance of E conditional on X. No, the variance of E is, the variance of E squared, substitute it in, start taking expectations, you end up with an expression which depends on S, not surprisingly. It depends on the variance of X, and it depends on the kurtosis of these epsilons. The covariance between them also depends on the both factor loadings and the variance of X. And so if you substitute the variance and covariance into the whole matrix of the covariance matrix of E squared, you get something which has this expression, which is exactly a one-factor model. It's got S prime, which is factor loadings. The average V over this sample period is V bar, and there is a diagonal matrix of essentially idiosyncrasies. So the key thing here is if V bar is equal to 0, then there's no geopolitical risk in this sense. There's no GEOVOL. And so we're interested in whether V bar is actually equal to 0 or not. But of course, we don't know the S's. But an easy way to do that is to ask whether there's a factor here. So we're going to do principal components here, and we'll be able to test the hypothesis that all these off-diagonal elements are equal to 0 or not. It might be worth noticing here that this matrix is an equicorrelated matrix if all these S's are the same. And so an easy thing to look at for equicorrelated matrices is the average. I mean, and it's sort of a sufficient statistic for that, is the average bivariate correlation. But it turns out an easy way to do this test is going to be looking at average correlations anyway, because, well, you're only testing sort of 1 degree of freedom as opposed to n or even n squared. But before I show you how that works out, let me talk a little bit more about how we're going to actually estimate this model. And I wrote down this data generating process. And from this EIT, if assuming that epsilons are normally distributed, we can write down a likelihood function for these E's, because the E's are the data. And the likelihood function looks like a standard normal likelihood function, except that it's summed over both cross-section and time series. And the difference from a normal likelihood function is we're conditioning as usual on the data that we observe, but this is also conditioned on the data that we don't observe. And this is a technique which, again, Hasty, Tibbs, Shirani, and Friedman called data augmentation. And they find that in a lot of these latent variable models, it's easier to write down the likelihood function, including X, that you don't observe, rather than to try to integrate X out of this density function when it has this sort of complicated form. It's also what we do when we do Fama-Macbeth models. We treat X as a series of parameters, and we estimate them as like they're dummy variables. And this is kind of what this looks like as well, but it's a somewhat different context. So the idea is that if we maximize this likelihood function with respect to both S and X, we will get something which is a useful interpretation of what we're trying to estimate. the S's are naturally thought of as parameters, but the X's are better thought of as a latent variable. And what the argument is that this is a lot like an EM algorithm where there's some data that's missing, and you're going to either estimate that data or maximize the likelihood function with respect to that data. This leads them to call this an MM algorithm, which is a maximize it with respect to X and then maximize it with respect to S and try to find a joint maximum. And finding a joint maximum means finding the solution to both first order conditions at the same time, and an iterative approach is a good way to do that. So we're going to propose estimating by, first of all estimating X, and then using that X to estimate S, and then using that S to re-estimate X and go back and forth till we find a value which is stationary, which therefore solves both the S and the X equation at the same time. So what do these look like? Well, the first one regresses E on nothing, but has a heteroscedastic term, which looks like this. It says in the cross section, each S is different, and therefore you can estimate X. In this cross section, you can estimate XT. So from the cross-sectional data on time T, you get an estimate of XT. And then you do this for all time periods. And then you go, okay, now let's estimate the S's. And from a time series, since we have an estimate of all these X's, we can estimate the S. So this is, you can use software like an arch model, but this is what you put in for the variance rather than an arch or GARCH or anything like that. Okay. There is a normalization which is required. We require X to be non-negative and with a mean 1. We require S to be between 0 and 1, but normalized so that, but we end up having to normalize it because if you remember this covariance matrix here, S prime times V bar, if you increase all the S's by lambda and you decrease V by lambda squared, you'll get the same covariance matrix here. So we have to restrict something, and an easy thing to restrict is the S prime S. That's also what happens in principal components, so it's natural to do that. So we're going to require that S prime S is equal to 1. And so the more assets you've got, the smaller the S's have to be on average. So let's now go to some what you might call results. There are two little Monte Carlos here and two applications. I'm only going to talk about the second application, and I'm going to only basically give you one slide almost on each of these Monte Carlos. We're going to be interested in the size and power of a test for volatility factor, and then we're going to be interested in the performance of the estimator of the volatility factor. When we look at the data, I'm not going to show you anything on the sector models, but I am going to show you world country MSCI ETFs. And so this is looking at co-movements across countries corresponding to the maps that I showed you at the beginning. So here's the size and power of the test for the average correlation being equal to 0 of the squared E matrix. And as you can see, this is the test that I'm going to show you. It's the one that I like best. It looks at the averages. And you can see when the size is supposed to be 1%, it's pretty close for either 100 or 1,000 assets for time periods for either 2, 5, or 50 assets. You'd get something that's all pretty similar. When it's supposed to be 5%, it comes out pretty close to that. When you're under the alternative, And of course, you have to know how far the alternative is away, but you see you get quite reasonable power anyway for the alternative that we've used in this Monte Carlo. When we look at the accuracy measures, I'm going to construct an R squared, which is the difference between the true X and the estimated X divided by the mean squared error of the true X and its true mean, which is 1. So this R squared tells you how much we've learned from the data about the actual X. And this tells you the same thing. How much do we learn from the data about the actual S? So here is this second Monte Carlo. There's the R squareds with respect to S, and these are the R squareds with respect to X. As N gets bigger, well, as T gets bigger, we get a better and better estimate of S, and we get R squareds which are very close to 1. So we get a quite good estimate of S when we've got, this is how many observations we're using more or less in the data set. Very good. When we look at the R squared with respect to X, they don't see much improvement going from T is 1,000 to T 5,000, but that's not very surprising because we've got now 5,000 things to estimate, and here we only have 1,000 time series to estimate. So we don't get much convergence here by increasing time, but we do get much improvement when we increase the number of assets. So this is a case where you need both the number of assets and the number of time periods to get large at the same time, and that's kind of what we see in the Monte Carlo. I'm going to skip the rest of it. Okay, how about now? Questions now?
Yes, Rob, we have 1 or 2 questions now. So I have one, but I'm going to call on Sophia Lee to ask her question. Sophia, if you'd like to unmute yourself, you can. Well, let me try unmuting. There we go. Sophia, if you'd like to start again, I think you may have been on mute at the beginning.
Okay, thank you, Andrew, for the opportunity. So my question is, why do we treat X as a latent factor? Can we just use the average volatility across country indices or global volatility as a common factor, given the strong empirical evidence that there is common co-movement in volatility in the cross-section?
So why do we treat it as a common factor?
No, why do we treat X as a latent factor instead of just using the average volatility across countries or the global volatility as the common factor, which is observable?
I think even if we thought that all the factor loadings were the same, we would still say that we only get an estimate of that from a sample we're looking at. So it's not something that we ever do exactly know unless we have an infinite number of assets, which are all follow the same model. So I think treating it as a latent factor is an attractive way of modeling that.
Thank you.
Okay, well, we had one more question that came up. So Abdullah Yalaman, I'll ask you to ask your question. If you'd like to unmute your mic, maybe. Okay. Well, Abdullah, if you can unmute your mic, you can ask your question. Maybe in the meantime, I'll ask my question. Robert, is there any evidence, maybe you'll talk about this in the empirical section coming up, of cross autocorrelation in these squared standardized residuals?
Correlation or in the square residuals? So
in the across asset, so like E squared IT and E squared J T minus 1.
Oh, okay. It's a good question. I think there might be. I don't think we've looked for it. One of the things we have seen is that there's a little bit of autocorrelation in our estimated X, which suggests that yesterday's squared returns, which are the input to yesterday's X, do have some predictability to today's X. And you'll see when I show you the dates that we picked that it's not too surprising that you find events which are close together in time may all be geopolitically important. But that would be good to look at that.
Thinking of like risk propagation of these shocks across.
Right. I mean, these shocks, because they're Garch residuals, there's no own lag effect.
Right.
So the lagged cross effect, I guess I would think would be small, but it doesn't mean it's zero. And there are a lot of them.
Right.
Yeah.
Okay, well, thanks for the answer. Well, I think I'll let you proceed. And Rob, you have about
I think I better keep going because I'm going to be out of time in
about 5 minutes left.
5 minutes, yes, okay. So in this data set, the standard thing we do, we look at the returns, which are in blue. We estimate maybe a factor model and then a Garch, and this is the Garch in red. You get standardized residuals in green, and we look to see whether there's still any volatility clustering here, and if there isn't, we say, oh, that's good, we've aced this model. We're going to look at something different now. We're going to look to see whether each of these are big whether they're big at the same time between Austria and other countries, for example. This is the first one in the alphabetical order. So first step is to estimate this model. We find that the average correlation for using these cross-country, so we're going to use something like, I think we have 45 exchange traded funds from different countries. We're going to use ACWI and the All Country World Index and the first principal component as the two factors. We end up with a correlation, cross-sectional correlation, which is actually slightly negative and not significantly different from zero. Then we square them and form a covariance matrix. And at that point, the average correlation rises to plus 0.08. And if you do a test, the test that I showed in the Monte Carlo, that produces a test statistic which is supposed to be normal 0.1, and the value of that test statistic is 120. So we're clearly strong evidence that these things are not independent. Here's what the little part of the covariance matrix looks like. You see 0.08 is not too different from what you're seeing in these columns, but the astonishing thing about this matrix is all the elements are positive. You don't see any evidence of one country's volatility being high when another one's is low. They're just all high at the same time, and that's what we're talking about. Okay, then we do these time series and cross-section regressions, iterate it to convergence, and I'm going to show you today for the first time results that are on VLab. There are results in the paper from this, but now we have an inference, which a model on VLab, which is updated, I guess, probably going to be weekly, but it runs all the way up to the present. And so here is kind of what you see. So first of all, this is the value of GEOVOL for the single largest event we see in the data set, which runs from 2000 to today. It occurred on March 9th, 2020, and it's when Italy was locked down and the Saudi Arabia and Russian oil price war occurred on the same day. That turns out to be the biggest geopolitical event in our data set at this point in time. You look down the second one, it's Brexit. Third one is part of the China trade war. Then we have COVID again. September 11th, 2001 is what the stock market did after it was closed for a week after 9/11. We got the shock in February 27th when the Chinese and European markets crashed, and the beginning of the housing price collapse. When the Chinese market collapsed on its Black Monday, and blah, blah, blah. Here's the Trump election in number 10, and more COVID here, and so forth. So you can see all these. If you go to the top up here, this is what you see as of now. But if you click on this or the left arrow, you can go to other time periods and see what does this look like at different time periods. If you look at the estimate of GEOVOL loadings, here are the loadings, the first principal component and the MCI ACWI index have the highest loadings, but only slightly higher than these countries, France, Spain, Italy, Germany, Netherlands. So a lot of these European countries turn out to be high, and I think that's partly because we're talking about what are common shocks, and we have a lot of different markets there rather than one big market. So you might think that a natural way to reduce your exposure to geopolitical risk would be to focus on these countries with low exposures. And I'm going to turn to that question in just a second, which is the sort of portfolio implications of this. Well, I guess it's right now. So if you've got these numbers, what are you going to do about it? Well, first of all, you probably are not going to be able to forecast when geopolitical events are going to happen, because it's basically almost a martingale. So the main solution in a portfolio strategy would be to reduce your exposure to these. And because these S's are not all equal, we can do that. So why would we want to reduce our exposure to GEOVOL? Well, a Markowitz optimal portfolio has a low variance, but it isn't guaranteed to stay low. In other words, if this low variance has a high geopolitical component, it may jump up and down a lot. And so it only looks like it's a low variability if you don't know what its exposure to the geopolitical risk is. And so you might want to diversify your risk as much as possible. And we think that there's a concept which we call risk diversification, which is kind of a desirable feature of a portfolio. So what does it really look like? And what's the theory of this? Suppose we have two assets with the same variance and same expected return, but one has a loading on GEOVOL and the other one doesn't. The Markowitz portfolio is going to be equally weighted between these two, and it's going to have a kurtosis which is proportional to the variance of GEOVOL. If you want to reduce the kurtosis, you're going to have to reduce the exposure to the first asset. So if you reduce the exposure to the first asset, you'll reduce your tail risk, you'll reduce the extreme movements, but you might take a little higher variance. And so there's going to be a trade-off between variance and fourth moment, which would argue that if you want to reduce your exposure to GEOVOL, that might be what you do. So I've worked out here, and I really don't think I don't have time to show you. But one of the things that happens is that this factor loading, this S that's in this case a factor, gets multiplied by the variance of this factor because it's a proportional factor loading. And so when we think about how impactful factor K is on your portfolio, we really might want to multiply this factor loading by its unconditional variance. And so S tilde is a variance-weighted factor loading, whereas the SK is the factor loading itself. So if you write down the variance of a portfolio with weights W, it has two parts to it. First part is multiplied by X minus 1, and the second part is the standard one-factor variance. And so if you want to reduce your exposure to X, you want to reduce this first part, which depends on the factor-weighted loadings of the factors, it depends on the betas, and it depends on the same thing for the idiosyncrasies. So I think we might be interested in portfolios which maximize expected return in a conventional way, subject to two constraints instead of one. One is that the overall variance is less than some parameter theta 2, and the other is that the exposure to geopolitical risk is less than some other parameter theta 1. We have a geopolitical budget, we've got a variance budget, and if this constraint isn't binding, we'll have a Markowitz portfolio, but if you add the second constraint, you will have a different portfolio which is tilted away from the high variance weighted factors.
If I could interrupt just briefly, Rob, if you could wrap up in the next 1 or 2 minutes.
I have one picture here to show.
Okay.
So when you look at the website again, we can get a comparison between GEOVOL. This is now going from 2001 up to the present. And let's see my screen. So you see this big spike here is the COVID experience where the GEOVOL really skyrocketed. In comparison, BlackRock has on their website a measure of geopolitical risk, which is in blue, which you can see is rising here, hits its peak during the European sovereign debt crisis and comes back down again, but is actually now, well, in 2019 was actually a little higher than it had been there. It was not so high during the financial crisis. It's been falling, and I don't know exactly what their view of the geopolitical, of the COVID is, but at least from this point of view, COVID is a very important example of geopolitical risk. There is the economic policy uncertainty scale, which is Baker, Bloom, and Davis, and that's essentially from newspapers, looking at keywords in newspapers, and that's in green. And you can see that was also at a very high level before the pandemic, and is actually now, again, at a very high level during the pandemic. The third is a geopolitical risk index that the Fed, a couple of people at the Fed have done, which is really more focused on a military thing. It shoots up during the 9/11 event, but doesn't respond to any of these events in here, and is low at this point. So that's an interesting thing to compare different ways of measuring this. And because there are different definitions, it's not surprising they differ from each other, but I think this is an important contribution to that. And so there is another way to manage geopolitical risks. And I think if what you really want to do is manage the shocks to a portfolio, measuring it as in terms of a volatility model makes a lot of sense. So I will stop here. Thank you.
Thanks very much, Rob. Well, we'll come back and take some audience questions after the discussion. Oliver, if you would like to share your screen.
I think Rob has to unshare. Okay.
Yeah, that might.
Okay. Okay, so let me just set my timer. Okay, so it's a great pleasure, of course, to make this discussion. So I'm not really going to bother with a summary because, of course, the paper's been exposited so well. So, but this is sort of laying some things out. What I'm going to do is I did try these methods or some of these methods out on a different data set, and I thought we'd just sort of walk through some of that. So in particular, I took the S&P 500 stocks, about 441 of them, data returns 2005 to 2015, fit a market model, devolatize the residuals, and then calculate all the pairwise correlations, either of the residuals or the squared residuals. So the red is the kernel density plot of the squared residuals, and the blue is the kernel density for the raw residuals correlations. So you can see from this that the pairwise correlations of the residuals are, centered around 0, approximately symmetric. A lot of them lie within a confidence interval that you might use for thresholding. So, there's not a lot of systematic variation there. Whereas if you look at the pairwise correlations, you do see most of them, nearly all of them are positive. And the average here is quite positive. So this is seems to be a fairly pervasive phenomenon that we can find in other data. So let me just move to the model, which is able to explain that. So this is looking at the standardized residuals from, in this case, factor model with diagonal Garch, has this multiplicative factor form. And it gives rise to the code movement in the volatilities of these standardized squares residuals. So this model does imply, if we take the strict version of this, where these epsilons or whatever that letter is, or IID, etc., that the pairwise correlations of the residuals would be 0, and the pairwise correlations of the squared residuals would vary according to these factor loadings S. And we use n loadings to fit these order n squared pairwise correlations, which is effectively what we do with time series when we assume stationarity, right? So it's quite a reasonable dimensionality reduction. And let me move on to the estimation. So this is all estimated by maximum likelihood, and it's a very nice procedure. I just carried this out by taking cross-sectional averages. And if you take cross-sectional averages of the squared residuals, you get an affine transformation of the latent factor. And the nice thing is that the slope of that affine transformation is positive, provided using positive weights. And therefore the ACF of this cross-sectional average is the ACF of the latent factor for any weighting series. And the ordering is preserved under this affine transformation. So in particular, the peaks. So if you want to look for where the peaks occur, you could just do it with this simpler weighted average. So let me just show you. So applying this to the S&P 500, and I'm using sort of Gaussian weights, sort of different draws from the Gaussian distribution, absolute value of, and then rescaled, you do find that the peak of this series is incredibly robust. I mean, down to the day, basically, the same value is picked out by taking this simpler procedure and calculating it. If we look at the ACF, so this is also very robust to W, and we find that the X factor is, for this data, is highly persistent. So this goes back to Andrew's question about the cross-order correlations. In this model, with this highly persistent X factor, should be manifested in the cross-order correlations as well, modified by the loadings, of course. Okay, so you can also do sort of time series averaging, but and there you would uncover the loadings up to an affine transformation, but the slope of that would be positive or negative or 0 depending upon the factor itself. And this is an estimation of so this is some transformation here. So you see the loadings are fairly spread out. There is a bit of a concentration at 1, which would correspond to the S's being 0, but it's not a heavy concentration. There's quite a bit of spread. So just sort of minor comment on the assumption of normality and cross-sectional independence. In that case, the kurtosis, so the sample average of the fourth moment, then is a quadratic function of the same loadings. And this doesn't seem to be, respected by the data. So there seems to be a role for some additional variation in the kurtosis, at least in this particular data set. So I like the testing, taking the average of the cross correlations, and it detects the sort of alternatives that are relevant for this model. I think theoretically, probably, there must be some cases where we have to take account of the preliminary estimation in the factor model, the mean factor model, and the Garch model, etc., to get the confidence intervals. But empirically, the model seems to work well. So. And of course, you can also test for the constant loadings using likelihood ratio or the averages that I put up. And this seems to be strongly rejected by the data. Some further questions. So can we relate these X's to global macroeconomic variables? Can we relate the loadings to observable country specific characteristics? And then the general premise of the model, I guess it's not clear to me whether the geopolitical risk should necessarily be symmetric, in the sense you could imagine, what's good for some superpower group is bad for another, and that also manifests in the risk. So it's not clear to me from first principles why that should be the case. The other question here is, I guess, how this sort of, you sort of you could integrate this perhaps with another model like a DCC model. I don't know whether that, changes the empirics. Finally, so let me conclude. I think I've probably shot my bolt a lot faster than I should have done. But I think it's a great idea, captures a very strong empirical phenomenon in a simple and workable model. It seems to work well in picking out the big events of our days. And the last sort of aside that I have is sort of reminded me of this earlier work of Cutler, Paterba and Summers, etc., who looked at large movements on the S&P 500 and tried to match those movements with, news stories in the papers on the subsequent day. And in that work, they found a lot of large movements were indeed associated with, economically relevant events, but there were also a lot that were not. So it might be interesting to go back and have a look and see how, because, apply this model to the same data and relate it to that literature. Anyway, that's what I have.
Okay, great. Thanks very much, Oliver. Rob, would you like to briefly respond to Oliver, and then we'll take some questions from the audience? And just so the audience knows, we're now at midday. I think we'll run 5 or 10 minutes late today. I didn't do the best job of keeping my former advisor on time. I take responsibility.
Well, thank you. Thanks, Oliver. That very interesting that you're able to put it together and make it all work. I am a little surprised at the strength of the geopolitical observation during the financial crisis, because I've defined these X's as relative to the predicted variance. In other words, just take squared returns divided by conditional variance. I mean, I'm not sure whether you did it that way or not, because that takes out a lot of the punch from high volatility periods. I don't know that there's any reason why it's better to do it the way I did it than some other way. So I think it's interesting to explore using raw residuals if that's in fact what you did. Or maybe it's just the fact that by using individual stocks, you see that same thing.
Well, I did devolatize with a Garch 1.1, but I haven't gone through and checked the results carefully, so I might have, some of the parameter estimates may have been way off. But
anyway, I thank you for doing that, and the questions that you ask are very interesting about how do you tie this to the macroeconomic events, and also of course Andrew's question of whether these shocks actually might have cross correlations too. So thank you very much. I'm looking forward to actually reading your slides more carefully.
Okay, well let's go to a couple of questions from the audience. It turns out we've got a couple of questions from your colleagues in Stern, Rob. They must be missing seeing you around the hallway. So the first question is from Menachem Brenner. I'll see if we can get, if you'd like to unmute your microphone, we can.
Okay, you hear me now?
Hi.
Yes.
Hey, Menachem, how are you?
I'm fine. No, I was writing, while I was writing my question, I realized that you start from 2000, and I thought that really big events that would be interesting, at least two come to mind, is October 1987.
Right.
And the other one is around the LTCM case in 98. So it's really interesting to see how those, you know, with your geopolitical risk, how those would come out. But anyway, I really enjoyed the talks, and actually Oliver was really referring to it when he gave his comments and so on. And it is interesting because it's something that some papers have already been dealing with it, but it's really a very open kind of question about geopolitical risk. And the interesting thing is, of course, as Oliver said, is to tie it to something that we know in terms of macro events, economic reasons, and so on.
Right.
That's it.
So I have not done any data sets that go back to 87. We've done in the paper, actually, it starts in 96. And I don't think LTCM does show up, but I can't remember what the events are in the late 90s. But if there's a draft of the paper that I think is now on the SoFiE website, and that has another top 20 list, which is a slightly different. It doesn't include the COVID period, so take that away and you get 5 extra spots in the top 20. So
Okay.
Okay, and we have one question from Steve Figluski.
oh,
Hi, you guys hear me? Hi, Rob. Hope you're enjoying the summertime.
absolutely.
Can't tell if you're in San Diego or New York. I hope it's San Diego for your benefit.
It is San Diego, yes.
Oh, that's good. That's good. You know, what you're doing is look at correlations among markets that are operating all over the world. And I wonder whether the factor that the X factors you're getting, are you imagining that they happen simultaneously at one moment in time in the 24-hour time? Or are we thinking maybe that, or might it be reasonable to think that there could be some kind of leadership? It could be like an American factor that then rolls around the world to the other markets. And one reason I'm particularly interested in this is a paper that just came across my desk. I haven't really had a chance to look at it carefully yet, but Oleg Bondarenko and Dmitry Muravyev claim that the entire impact of a day's events on the ES mini futures contract, which is the futures contract tied to the S&P 500, it all happens in the 4 hours between the time the Asian markets are closed and the European markets open. And after that, nothing else happens. Nobody understands this, but it's empirically seems to be the case. So anyway, I wonder how this might affect what you guys are doing.
So what I've shown you today is ETFs, which are written on all these international markets, but they're all traded in New York. And so we're using New York closing prices. So there's a synchronicity in the returns, which would reduce the effect of this, but it may not really be the only or the best way to even deal with this. We've also done work where we use indices, which are therefore have closing prices in the local markets rather than in New York, in which case you have to deal with the fact that what you mean by today is ambiguous depending which market you're in. And so you have to do a specification of how that gets split up. Now, it turns out that you get pretty similar sort of results from either treating the asymmetry, the asynchronicity parametrically, or using using all assets which are closed at the same time. But obviously there's a richness there that we're not yet exploring.
Okay, well, I think that might be a good place to end it. We're running a touch late. So let me thank our speaker, Rob Engle, for a very interesting talk today, and Oliver also for a very detailed discussion implementing these models and taking it to data. And before I finish, let me do a small advertisement for the next SoFiE seminar. So 2 weeks from now, we'll have Ying Li from Hong Kong University of Science and Technology presenting, and her discussant will be Professor Michael Wolf. So please join us in a couple of weeks' time for the next SoFiE seminar.